The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to the presentation. Where is it? I'm Michael Green. Or Billy, were you introducing everyone? Sorry about that.
No, I was just going to do a couple of housekeeping things here, so I'll turn it back over to you in just a minute.
Okay.
I want to say welcome to the APA Standards and Codes webinar series. My name is Billy Zidek. I'm the Codes and Standards Administrator. We have a couple of housekeeping items to do. This webinar is being recorded. The recording and presentation slides will be posted on our webinar page on the APA website in a few days. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received during the Q&A session. If we run out of time, we still have questions, responses will be sent directly to the person asking the question by the presenters. Continuing education credits are being offered for this webinar. Please contact me at Billie, B-I-L-L-I-E, @appa.org for more information. Also, if you have more than one person attending the session from a central location, please contact me so everyone gets credit for attending. At this time, it's my pleasure to turn this presentation over to Michael Green and David Raker.
Hi, everyone. I guess I jumped the gun a little bit there. But again, I'm Michael Green, Director, Energy Management, Infrastructure, Facility Engineer for University of Toledo. I've been with the university for about 16 years, so I know the inside and outside of all the buildings, run projects, a lot of mechanical infrastructure, which is going to lead us into this transactive energy implementation study that we did here on campus. Dave Raker, he really is the meat and potatoes, the grad researcher. He's been with the project for the whole year and a half. He's going to get into the details, which will probably interest you. So I'll give a quick overview about UT and get us from the first slide and into Dave real quick here. So several of you may be into energy, and everybody's into saving money or increasing our sustainability on campuses. This slide here is the utilization index for the campus. All our data for our buildings are online at the University of Toledo Facilities and Construction Sustainability page. If you wanted to get more data, it's there, it's open for the public. But basically, UT was picked for the implementation study because of the robust controls infrastructure that we already had in place. Back in 1985, well before my time here, they started with centralized controls, and they were working to get to primarily a single source system, something that is easy to use. Along with that comes the complexity of being a public institution, of how to competitively bid, which would be a separate discussion, but we managed to fix pricing so that we could provide safety, comfort, and then, like I like to say, I'm third, efficiency. Now, looking at this graph, you can see the tan bars in the background represent the square footage across campus, and our square footage has increased over the last 14, 15 years. But the significant thing here is that it didn't just increase in like warehouse space, it increased in lab space and clinical space. And we changed conference areas into clinical and lab space. So we become highly, highly intense use per square foot. Now, if you look at the top line, that represents the hospital, and you can see that it went from about 298 down to 228, or a 23% reduction in energy over the last 15 years. That's significant. Diving down further, and I got information. If you have questions, I can talk to you later about how to. But diving down further, you can see that the blue line there is the main campus, and it went from just a 112 to a 102. And what's significant about this is that other campuses talk about making a 20% energy reduction, and they're boasting a 110, 120, or a 130 EUI per square foot. We're significantly below that. Again, it's because we've been working on this since 1985. and we've made great strides at it. We're running very lean. So when it came to Scott Park, which is the bottom line, PNNL and the DOE came in. We have a solar field there. We have wind turbines there. We have LED lighting, and we had this robust control system. And everything was already set up for a good transactive implementation study. And the tricks and problems that come with that were a lot easier because we already had the infrastructure. We are a facilities group that works with the professors and the rest of the campus. We don't look at ourselves as a standalone facilities, just doing facilities and construction. We're an integral part of the university. So when they said transactive controls, well, first we had to figure out what transactive was, and that was confusing. But in sum, just for a facilities guy, it's basically one VAV box talking to another VAV and exchanging artificial or real currency to provide that comfort cooling for the occupants. And at that level, it gets pretty complicated. And I'm going to hand it over to Dave now to get into more about the transactive controls. Dave?
Hi, my name is Dave Raker. I am an electrical engineer and I'm a graduate researcher here at the University of Toledo. And we are working on this campus Transactive Energy project. You can see here an aerial view of the Scott Park campus, a small satellite campus of the university. Has 8 main buildings, 6 of them connected by a common corridor. And we have, over the last 2 years, integrated in the 2 photovoltaic arrays you can see there in the background, and a large battery system, which is off screen to the right, into the building systems at the Scott Park campus. There is also a couple wind turbines there. We don't have them in what we're doing yet, but the first couple of years of our project we're largely integrating these and testing out the software and algorithms and all of that. And as we move into the next phase of our project, we're now working on use cases for transactive energy. And we'll talk a bit later on about what that means. So, well, first of all, why would we want to do this? The purpose of this project is to integrate these buildings and this equipment with the electric grid. But why would we want to do that? So from the grid's perspective, as more and more distributed energy resources come online, protecting the stability and the integrity of the grid becomes more of an issue. And so we start to look at smart grid technologies that allow communication and collaboration between all of the different entities connected to the grid. From the perspective of the campus, we're interested in energy efficiency. We're of course interested in cost management, the comfort of our occupants, and of keeping things working well. And this sort of system can help with all of those things. So just a quick little bit about the equipment we're actually working with. As I said, the Scott Park has 8 buildings. They were largely constructed in the late 60s and early 70s, the last piece in the early to mid 90s. In 2010, a couple of photovoltaic arrays were installed, a total about 1 megawatt, and those are on a power purchase agreement with an outside entity that sells the university the power from those on a sort of rent-to-own program. And we added a battery energy storage system, which I'll refer to as a BESS. It's 130 kilowatt hours of storage, which is relatively small in terms of the whole campus. It has 125 kilowatt power capacity, and that was just installed 2 years ago now. So the building automation system that we have is a Siemens system, and there's a central top-level controller for all of the campuses that all come together. We have, that should actually say 8 field panels on the Scott Park campus. There's 6 energy meters, and I got my numbers crossed there. There are, I'll talk about the number of zone controllers in a little bit. It is all electric equipment. When this was installed, they didn't put in any gas. We mostly have VAVs with electric reheat. There's 16 air handlers on the campus and a campus-wide chiller plant. The rated power on the campus is around 4.6 megawatts. The actual average load is about 730 kilowatts. The photovoltaic arrays are cadmium telluride panels from First Solar, which is a local company here in Toledo. Yeah, well, they're actually based in Tempe now, but their manufacturing is still here in Toledo. They started on our campus. And yeah, the rated power of that is 1.1 megawatts DC, or just under a megawatt AC. Average daily generation of 3.45 megawatt hours. Our battery system that we installed, you can see it getting dropped off here, is a big shipping container full of lithium-ion batteries, which you can see on the left-hand side at the bottom. That's the rack of modules, the inverters over on the right. And we've already gone through, I think, the important specs for that. Yeah, but there's more detail here if anyone wants to look at it later. So to bring all of this together, we use a piece of software from Pacific Northwest National Laboratory called VOLTTRON. And VOLTTRON is a distributed sensing and controls platform. Makes it easy to integrate equipment from lots of different systems that might not normally easily talk to each other. It has cybersecurity in mind from the beginning. And some of the reasons that we're installing this instead of simply putting things together through the existing building automation system is that this allows us to run analytics, store large amounts of data, integrate with simulation frameworks and such, things that wouldn't be as easily available without taxing the existing systems. Although the sort of control strategies we're testing are things which we might eventually see coming into building automation systems by default in the future. Yeah, so VOLTTRON is put together a bit like this. It's built around a message exchange bus where data from different sorts of systems can all come together in a common format. It has drivers for talking to various different types of equipment and for interacting with services out on the internet, or for pulling data, actuating data, storing data, and most importantly perhaps for writing applications which can be run in this environment that don't need to know about all of the intricate details of how any of these systems work on a lower level. And the network that we've put together of this is laid out a bit like this. This is a big graph with a lot of stuff on it. But the important thing here, the beige nodes, hopefully you can see my little pointer here, that kind of form an arc through here, are our VOLTTRON instances. These are mostly Raspberry Pis, very small little computers, about the size of a credit card. And they are running VOLTTRON for communicating with various equipment. Each of the ones in these arc is handling one building level meter and 1 to 2 buildings. That is one, or equivalently 1 to 2 field panels within the building automation system, and are pulling data from the meters over Modbus and from the building automation system using BACnet. The photovoltaic array and the battery systems both use Modbus for communication. The photovoltaic array is not controllable. We're only pulling data from that and storing it. And the battery, of course, is controllable. It wouldn't be very useful otherwise. In fact, our controller for it is written as a VOLTTRON agent and runs on this node that talks to the BESS and communicates with it over Modbus. Now that data all comes into a centralized instance that runs what we call a historian. That pushes everything over to a database cluster where it's then accessible to us outside the facilities network from a visualization node on which we run Grafana. And we also have a node which is able to talk, which is running VOLTTRON and is able to talk out to the outside world for communicating with other entities or collecting data from the internet. In order to actually bring everything in, our buildings, as I said, are running, well, they're not running BACnet natively. We're communicating with them with BACnet. Natively, they're running a proprietary protocol in the BAS, and we're using a piece of software within the top level controller for the BAS to translate everything over to BACnet. Now, if these were native BACnet devices, VOLTTRON could talk to them directly. Alternately, we could have written a different driver to do that, to talk to the native protocol. VOLTTRON is extensible that way, but it was a lot easier to do things like this. And that actually gives us a little bit more control over how we work with it as well. So the configuration for it is pretty straightforward, and I won't dwell on the details here, but yeah, suffice to say that we basically make a table of all the points that we're pulling in, one table for each device, and we stick a little config file saying which table goes with which device, and that maps all of the data coming from the BAS over to native points within the VOLTTRON environment. The points that we're actually pulling in, we have 237 zones. Of those, 152 of them have electric reheat on VAVs, another 48 which also do, but also fan-powered VAVs, and then a small assortment of other things. Most of the non-HU connected ones have their own cooling loops. They're installed in additions where the air handler doesn't get over to. The building systems are being pulled once per minute. We're actually pulling 8,551 points once per minute. The building meters we're pulling a lot faster because we're often interested in power more than energy. We're pulling those once per second, and the campus meter we're actually pulling once per second, so it can keep pace with what we'll see for the PV array in a moment. So altogether, we are actually pulling about 12,500 points per minute into VOLTTRON, and storing those to analyze things later or to do things in real time. We could actually improve our pull rate if we were installing this now. VOLTTRON does now support the change of value functionality that's available in BACnet. And hopefully, I need to talk to Siemens as to whether or not this is compatible with their stuff, but hopefully we'll be able to move over to that in the near future. As far as how we actually control the writability and the priority of things, of course, everyone wants to know how it's going to interact with the existing systems. When we went to configure that, we marked specific things as being writable in the configuration. Otherwise they're not. And we're typically writing with a BACnet priority of 14, which is more than the default, but much less than what operator overrides would usually be about an 8. Lower priorities or higher priority, for some reason. And so we're not overriding anything which would be set manually. We're overriding automatic control when we do so. But of course, we want to consider the cases where we don't want things to be left in a writable state. And VOLTTRON does actually integrate a fair number of facilities for making sure that communications stay sane and that we're not doing things which hamper the normal functioning of the building automation system. So whenever we have been writing to things, the drivers will automatically revert them to their original value. And VOLTTRON by default has heartbeats for letting the BAS know that things are operating. If they stopped, and the BAS knows to take back control. And there are global overrides that can be set, which will force VOLTTRON to stop communicating with the BAS if control needs to be taken back at the building's level.
Dave, let me interject for all the facilities people out there right now. That this slide is important more than the Douglas Adams reference on the side, is that when Dave's talking about the VOLTTRON, it's on top of your automation, whatever you've got in your existing. And the heartbeat is critical so that it's only going to control the set points that are out there. And it's working back and forth amongst the individual devices, changing those set points for that transactive piece. But if it ever had a problem, that heartbeat, the signal coming back would put it all back under automated, whatever the logic system that you've already got in place, and your occupants wouldn't see a difference at their end. So we protected the occupants first so that things don't get out of control, even though we're applying this as an energy reduction resource.
Right, and we also do have controls in place when we're actually running algorithms to make sure they're not changing set points more than usually about 2 degrees in either direction. And rarely do they actually reach the limits of that for anything that we're trying to do. And we're usually not looking to see a difference in the actual temperature that things are keeping. We're actually looking to see if there's not a difference typically. So when we go to integrate the PV array, we had to actually make some changes to our network in order to bring it in. As I mentioned, this is actually under a power purchase agreement with another company. And so we did need to work with them. It has its own dedicated collection node, which sits out in the field near the PV array. And we were able to bring in a dark fiber that was already installed between the PV array and the buildings, which wasn't being used. As it looked when we got to it, the two arrays were completely separate. Each is communicating out with the SCADA provider that manages those arrays using a cell modem from the field. But there was conduit there with a fiber, which we were able to bring in, install some Ethernet switches, and convert things over from Modbus RTU to Modbus TCP, which allows us to have multiple access to it, so we're not interrupting anything that they do. And now we're able to bring that energy in directly, or excuse me, that information in directly. We're already getting the energy. And we are actually pulling a lot of that data. The important stuff we're pulling once per second. When we're looking at the PV array, we're very interested in rapid changes in power that happen on that. And so for irradiance and power readings, we're actually taking those very fast. And things like temperature and state of the inverters, we're pulling a bit less frequently, more like the buildings. Now the battery system is brought in a similar manner. We have a Raspberry Pi sitting in the field. It has, as with the PV array, they each have two network ports, one going onto a private network that doesn't touch the rest of our facilities network, and one sitting on the facilities network where it can talk to the rest of VOLTTRON. For the battery system, we actually have the top level controller of the battery running as an application, an agent as it's called in VOLTTRON, and that is taking data from the battery system and the inverter and the meter in there and sending back control signals from that. The battery agent that we wrote that controls that is a fairly simple state machine, and for the time being does manual control. Now that's manual from the perspective of applications which are running automated algorithms. But eventually we will probably add some modes for handling other things which are part of the MESA standards, for instance, following frequency watt curves or things like that. But this gives us the ability to send charge and discharge signals to it, and it manages any faults and warning conditions that the battery might have, and propagates that up to us where we need. This is, by the way, publicly available, or it will be. I don't think the pull request is actually fully through yet, but that will be in the VOLTTRON GS repository on GitHub. GS is for grid services. And if anyone wants to go looking for it now, it is on my GitHub, which the username is just David Raker, all lowercase, and it can be found there already. That is released under an Apache license if anyone's interested in using it. So we'll start getting into applications of this and why we're actually interested in doing this and what we're doing with it here. But one thing to quickly bring up is that this has had some nice benefits for fault detection. And VOLTTRON has various automatic fault detection algorithms which can be installed for it, and monitoring and alerts which you can set up. But here we were actually looking at the flexibility of our buildings for other reasons, and we were able to use this as an active fault detection technique and get a lot of data back to our facilities folks on things that in many cases they weren't actually even aware of needing to be addressed. So the normal building automation system, while it's able to keep trends, doesn't normally have a database with trend information for every point within the system, but we do. And so here what you're looking at, we were sending a test signal to every zone on our buildings simultaneously, where we were pulling up the set point by 2 degrees and then setting it down 2 degrees from where it was already sitting every 3 minutes, and watching how the various systems responded and how that signal propagated through from beginning to end. Now this zone is working. You can see the airflow in the VAV changing in response to the cooling output loop here, which is responding exactly as we'd expect it to the changes we're putting through. Now, one thing to take note of is the flat yellow line here. That's the actual temperature of this zone. We're not doing anything here which is affecting anything anyone's going to feel in the building. But what we can see is when things are not working. So here's a zone where, for whatever reason, that damper isn't moving. And I'm not showing every step along the way here, but we can normally see this go, through the cooling loop. We can see changes in airflow, and we can see changes in power. During wintertime, of course, we see changes in the usage, the duty cycles from the heaters in the building. But we were able to identify actually a couple dozen minor problems that were being hidden by the PID control on the buildings. Because of course, the zone next to it steps in and compensates when something isn't working. And we were able to give a nice list of things for them to take a look at. And a lot of that can actually be automated if you set up some of the automatic fault detection stuff. So looking at demand side management, I mean, this is the main focus of our project, is looking at how we can manage things which are important, not only to the campus, but also to the electric grid from interactions inside the campus. So when we talk about demand side management, we're talking about the loads in the grid being used to help manage the actual flow of power and structure within the grid. You always have to keep a balance between the amount of power that's being generated and the amount of power that's being consumed. And if that balance comes out of whack, then you start to lose the ability for the grid and the devices on it to function the way that they're supposed to. And there's the slide that I was thinking I had first here. This is the sort of thing which happens when you don't keep a balance in the grid. Some of you may remember a big power outage throughout the whole northeast of the continent. Actually, it wasn't just the US, in August of 2003. I certainly remember being without power for a few days. And you can see a lot of just dark spaces where Toronto and Detroit ought to be. For those of you not aware, this entire power outage was caused by a tree striking a transmission line near Akron. But without the flow of power that was already at its limits from one part of the grid to another, power plants had to start shutting down to protect themselves. Once they shut down, there is very little that most of them can do to start back up. Big turbines actually require external power to get spinning again. And so in addition to anything which needed to be repaired, there needs to be power available to bring all of these things back online. And so as the problem gets more complex, where we have a lot of additional generation, where you no longer have a single few generators with a lot of unpredictable loads, and you can manage those generators based on what the loads are doing. Once you add in tons of distributed generation, which is by itself unpredictable, it starts to become a computationally very difficult problem to solve. So going back to the somewhat more general level about this, there are three basic strategies that you can take to manage things on the demand side. You can have a commanded response, like we're showing here. Decisions are being made over on the left-hand side, on the supply side at some interval. And this is a demand response type setup, which we'll talk about in a minute, where the supplier has to have the capacity of the demand participants to participate in mind ahead of time, and it will actually send commands as to what it expects them to do, and they need to implement that. And of course, you have to keep a fair amount of reserve still. This helps to reduce the amount of reserve they need to keep of spinning generators to handle fluctuations and such. But you still have to keep quite a bit, because you never know when people are going to actually hit those targets. Another way of doing it is to provide an incentive. I think everybody probably is familiar with the demand charges. which large consumers have. And this is an example of that. You have some sort of rate schedule that's set ahead of time. And on the demand side, you are attempting to optimize your cost by trying to stay under whatever thresholds you need to avoid the penalties or to gain the incentives that you're being given. But this doesn't really give any information back to the supply side other than what was actually achieved once it is. Though it does have the advantage of being a little bit more steady state. When someone's implementing these things, they're typically implementing them all of the time. And then we have what we are actually interested in looking at more than anything else, which is what we call transactive energy. So the idea here is that you have a lot of different actors on the grid: campuses, buildings, utilities, generators, other utilities, industry, residential. In a smart grid scenario where all of these things can communicate, they can start to act cooperatively in order to manage the grid in a distributed way where it doesn't require having a centralized optimization that becomes overly complex. And though this diagram looks more complex, the important thing to keep in mind with this is that the only thing being exchanged between these actors are price and quantity. How much am I going to use, and what is the price that I'm going to be charged for it? And all of the internal information that these have stays within each entity. So the campus isn't sharing what its capacity to curtail is with the utility. It's simply the utility is giving it a dynamic signal, which the campus can respond to and say, well, then this will be my quantity. And if the utility needs to adjust its signal, it does it on the basis of the feedback that it's constantly getting. So that this is more of a closed loop with regard to the entire electrical infrastructure. And within each of these actors, it's actually much more simple because it doesn't need to consider anyone else's criteria, only its own. So let's look at a few particular use cases, and some of these are things which we have implemented on the campus or are in the process of implementing or improving our implementation of. Other things are a little bit forward-looking. One of the key use cases, which is of interest probably to folks in facilities, is managing demand peaks. You want to avoid those demand charges, and if you, like the University of Toledo, is participating in demand response, it can even be a source of revenue for you. The university has manually been implementing demand response for the last 2+ years and earned about $300,000 a year on each of those, and hopes to do about the same going forward. And that is done where a signal is sent from the utility that a curtailment is needed, and they have loads which they're going to manually shut off to do that. Now I'm going to talk a little bit about the ILC algorithm from PNNL, which is one of the things that we've implemented on our campus. And one of the things which is available for, I know there are actually some commercial entities that are making use of it in similar ways to some of the use cases we'll talk about. That's intelligent load control. And it is a hierarchical analytical process, analytical hierarchical process, I believe it's actually called, which is basically a way of looking at a priority matrix for all of the different zones within, say, a building, and choosing which zones are the most capable or are going to be the least impacted by changing their power usage. And instead of just simply across the board cutting off, say, lower the set point for everything 2 degrees, or turn the air handlers down by some amount, we can look at who actually has the most capacity right now and manage the buildings dynamically, automatically, in a way where it's going to have the least impact on occupant comfort based on current data coming in. So in that case, we're getting a quantity commanded to come in, and we're using that to figure out what threshold of energy we would need to set, and then ILC manages which loads can be shed and when, and it will do that dynamically. And so if we are looking at a demand charge regime, where instead of getting some signal, we have a rate schedule. This is more the case that ILC was originally developed for. And we're choosing some target threshold at the beginning of the billing period and trying to stay underneath it. And each time that we can't do that, we'll step up that threshold. We're already going to be charged for it, but then ILC will attempt to manage loads, keeping them under that threshold progressively, and hopefully we'll get the lowest threshold we can by the end of the month. Well, not hopefully. We necessarily will get the lowest we're able to get that way. So this is an actually example of ILC in operation. What you're looking at here are some panels that we see in Grafana. We can actually see these in real time as they're coming in, or we can look back on them for historical data. So this red line here is the threshold that we set at this point in time, is 50 kilowatts. And you can see as the power meter in the building reaches that, it's very quickly being brought back underneath it, and it actually comes up to it a few more times, and each time it's being kept underneath it as well. And it's doing that by choosing some number of zones. Looks like there are a maximum of 5 in this case that were curtailed at one period in time. And it shows those zones based on which ones were going to be the least affected by being able to curtail. And while we do see a tiny bit of a movement here in temperature, it's minute. We're looking at less than a degree here. A lot of times we don't actually see any movement at all from these. Now they do have a new version of ILC which is able to handle bidirectional criteria as well, which we're going to be testing out in our next phase here. But why would you actually want to augment your power use? I mean, we're interested in saving money. We're not interested in spending more money. But the thing is that power use isn't typically uniform throughout an entire day. You have times of day in which you know that your draw is going to be a lot higher than others. And it is often possible to shift those, the times at which you're powering certain things to different times of day if they're not going to be as affected by it. And we'll see that a little bit more when we talk about PV variability. Pre-cooling a building for a few hours is relatively hard to do. But if we're talking about shifting loads for a minute or two, while we're looking at fluctuations in power, that becomes very easy to do, and no one ever is going to notice it. So let's say that we want to set up a transactive network. We do here. We're setting one up, and we have one set up actually, and we're starting to test it out. And we want to manage these peaks in a transactive way. So the funny little arrows on here, by the way, are pointing from the ball into the socket. That this is I guess a UML notation. But it's actually an E3 use case diagram showing how different value objects are being exchanged by the different parties that are participating in this transactive network. And so we're representing. Oops, I just lost my place here. We're representing our demand charges now as essentially an allowance for peak power usage, and we're paying some price for some allowance. And that can be handled in a few different ways, with the campus aggregating that into the cost, which is being passed along to lower hierarchical actors, or by passing it directly through. And there are cases where you might want to do either of those. We'll see a little bit more of the intra-building stuff in just a second. One of the things that we've done a lot of is working with the mitigation of solar variability. And there are a few reasons why that's important. From the perspective of the grid, it's a stability issue. You have to keep reserve power in place in order to manage spikes and dips in power coming off of large amounts of distributed generation. And while there's a degree of averaging that happens when they're spatially spread out, that's not really very helpful for particular legs where you might have a lot of variability coming from a large plant onto the grid. from the perspective of the campus, this is going to contribute to your demand spikes. You have this great resource. You have this photovoltaic array, you have wind power, and you're bringing in renewable energy, and you don't need to buy it from the electric grid when that happens, and you're happy because it's lowered your demand charges, and then a cloud goes over the sun, and suddenly you have a demand charge again. But not if we can control that. There are a few ways that that's done in practice, and I need to hurry up here a little bit, so I'll start speeding through a little. One way that things like this are handled, often less for variability than for overgeneration from utilities to utility scale generation plants, is by controlling inverters. We don't do that here, but it's extremely fast and extremely effective. You can move the power point on the inverter and simply not have generation that otherwise would have been available to you. But of course, you're losing that power. It'd be much more efficient if we can, say, use that power somewhere else or reduce a different load. But the PV inverters are very quick to change, whereas a spinning turbine has a time constant to it that takes a long time. So we've worked with a few different PV variability mitigation algorithms. This one shown here is taking sensor data and an irradiance forecast. We're using a smart persistence model to look at what we expect power to be in the next cycle, passing that through a model of what the PV array is going to do, and choosing an amount of power to mitigate from each of the participants, whether they're buildings or the battery system. The battery system can respond very quickly and effectively to these sorts of things, even without all of that. In fact, this graph is actually showing a different algorithm that we use, which is looking at actual power coming off of the array and using a sliding window on a moving average to, when you have a longer window, you have more smoothness. You don't need these large spikes at all if you're willing to spend enough energy from the battery to make up for them. But you also are going to require a much larger battery with a larger window. And so ours adjusts that window based on how quickly or how much variability actually needs managed at a given point in time, and it makes much more efficient use of the battery that way. We'll be publishing on that hopefully here shortly. And you can also actually get the buildings to participate in this. I always laugh a little bit when I see these diagrams because we have some things electrical engineers love to do, representing things that are absolutely not electric circuits as an electric circuit. But what we're actually looking at here is heat flow through a building, where inputs are being represented as current or voltage sources. The outside air is a voltage source because it's a gigantic sink or source that can't really be changed by what's going through it. And the heaters and irradiance coming through the windows provide essentially a heat current. And you have some time constant by which heat is going to escape from your building from the heater to the inside air, through the envelope of the building and out to the ambient environment. And that allows buildings to actually act as a bit of a battery, especially when we're talking about something very short term. Obviously, your building is going to lose or gain heat more quickly than we'd like it to. We'd all love to have perfect insulation. But when we're talking about something like PV variability, we can change power pretty dramatically without losing what the state of the building, as long as that's happening in both directions. And when we start looking at how we can plug this into a transactive network, we can actually look at this variability mitigation as a service being provided to the grid, we could model it instead, similar to how demand charges are modeled. But we'd rather like to see it as a service, right? We get paid for those. Where we provide some amount of mitigation. We keep our variability under some threshold, and that's a nice service that we're providing. These services don't exist yet, though they're an example of ancillary services, which many of them are currently in place. And if you have generation, you can participate in these. It's of a certain size, and even if you are a load, in some places it's starting to become available where you can actually participate in controlling the parameters of the grid and potentially even gain a revenue source for your campus. by being able to adjust your load in order to manage things in real time. Now, these are very, very short-term markets, usually operating on the scale of seconds. But for example, in the graph we're showing here, you're adjusting the power, in this case from a battery, but you can also do that, as we said, by changing the load on buildings or by changing the inverter on generators, in order to bring the nominal frequency of the grid back to where it's supposed to be. Well, the nominal frequency is moving the actual frequency of the grid back to the nominal one. Because if you're not aware, the grid has to remain at a certain frequency or stuff breaks. And as you add or remove power from it and things are not in balance, you move above or below that. And you can do similar things with reactive power. Those markets exist, and for moving peak loads and things like that. And this is very similar to the variability model, so I won't spend any time on this, but you can look at it later if you're interested in looking at my presentation after the fact. But again, we're selling a service in exchange for following some curve on the part of the battery, shaping loads on the part of the building, which allows us to move left or right by changing our power up or down here on this graph in order to get the grid back to where it's supposed to be. And that's something that the grid operator needs. And so the way that perhaps in the future, if it's not available so far in your area, you can actually make use of. And one last area to quickly touch on is that these sorts of markets don't actually have to have real exchange of money. You can actually use these as control algorithms for operating within your buildings, for especially in the case where you have tenants. And that might be department or division boundaries, and you can encourage more efficient scheduling of resources, help to modify occupant behavior by internalizing the cost of actually using energy onto people within your buildings.
So Dave, this is a good time for me to interject it. So going back to the beginning where I was talking about the campus utilization index, and that UT already has a very flat, and we're still implementing more LED on campus, and we're working at progressively tightening up the controls. So again, it's behind the scenes. So if the occupants don't really see it, but the campus sees a robust savings in the supply side or the demand side. But the VOLTTRON going on top of it, someday I can see that all automation companies will have something like this buried inside their program. But in this case, trading zone to zone can help us get to that lower EUI, so we can break that 100, which would be the magic number for us. Or if you were up at the 120 or 130, it could help you accelerate even further. And again, this is offered from third-party companies like the Base IoT that was mentioned here, and Andrew might want to interject. But basically, from our point of view, this would be the next evolution of controls for us on campus, and it's going to make us more user-friendly in our community and provide us a better price point for our utilities.
Yeah. And with that, I'd actually like to turn this over to Andrew real quick. I've gone a bit over the time that I should have. So Andrew's going to talk a little bit about VOLTTRON and what they do over there.
Great. Yeah, and I will go very quickly because I think the viewers here are probably going to have a lot of great questions based on your presentation. That was really great. I'm Andrew Rogers. I co-founded Ace IoT Solutions last year based on some work that I've been doing with Eclipse VOLTTRON for the last 2 years, primarily around the city of Washington, D.C.'s commercial deployment in their building systems. It's been really great, actually, to see, and one of the reasons why we helped try to get this webinar to happen was seeing David's presentation at the VOLTTRON Summit this year, It's a very exciting application, and we want to see more of this stuff in campuses across the country. I'm going to talk a little bit kind of from a high level what we see as some of the values of VOLTTRON. You know, we hear a lot about open platforms and open communications frameworks in controls. And I think one of the values of VOLTTRON is not just that it's you know, an open standard or implements open standards, but it's a open source platform that's accessible, available, and it implements a lot of open interfaces that allow you to tie things together, like battery energy storage systems and building automation systems and PV, et cetera. There's a pretty good community in the campus use case. DOE supports this pretty well. There's starting to be some commercial support from companies like ourselves. Oh, I've been going through slides and no one can see. I'm sorry. I think David hit this a little bit about the security by design. Obviously, coming out of the Department of Energy system, one of their key focuses is cybersecurity. So having the insight and expertise of the national labs behind you in looking at custom or novel implementations of control systems like David laid out, having them behind you on the security and the robustness is really good, especially if you're a facilities person going to your technology department to talk about implementing some of this stuff. A lot of the questions that you might have, that David illustrated in the network design have been answered through this ecosystem. Another thing that was touched on that we think is really important in these campus environments is that because it was also built around sort of deploying research level applications in operational campuses and facilities, the Failsafe functionality that David and Michael talked about is built in. It's been running in DOE campuses. It's been running in Washington D.C.'s municipal campus, portfolio for years now. There's a history of it being reliable and robust for facilities, as well as enabling these really interesting novel applications. David just talked about a bunch of different demand distributed energy resource applications that UT is doing, which are obviously very interesting. And of course, we plug ourselves here. If you need help, a lot of the stuff, and one reason why we're so excited about UT specific implementation is a lot of the components on that graph that David showed are things that we helped the VOLTTRON team develop from the perspective of building out Washington D.C.'s platform. And just to go through a little bit of the broader world of what is available in the VOLTTRON ecosystem. So the DC implementation I talked about has got VOLTTRON in about 60 buildings, pulling in data. They use it simply to get all the data in one place and then manage the building state on an ongoing basis. So the primary driver for them on this project was they were investing a lot of money in recommissioning, and they were seeing that over time they would have a big jump in performance of the building when the recommissioning happened, but then in the next 12 to 18 months they would see those buildings sliding back to a poor level of performance. So they use the central data platform to keep an eye on everything, understand which direction a building's is trending, and then jump in and provide lower cost interventions before it gets to the point of needing an entire recommissioning. There's a really interesting application right now that we've got a blog post on our website about with Southern Company and Oak Ridge National Lab, where they're doing distributed energy resource pilot with 2 neighborhoods, one looking at community scale integration of community scale solar and battery storage, and another one looking at sort of per house resources that are all taking the same transactive approach to management. Thailand has done some really interesting things, building out sort of some pilot smart home implementations. We see data analytics companies and your mechanical service providers as being interested in this platform by providing a universal data platform that allows that visibility that David and Michael showed off, Even into simple things like, oh, you've got a zone controller that's not responding in the way you expect it to. And then we do a little bit of work with renewable energy companies as well. Those value-added services of transactive energy and grid correction from the inverter perspective, those are all things that VOLTTRON lends itself very well to providing a platform for. And so my takeaway is, if y'all have, what I would love for y'all to walk away from this, thinking about VOLTTRON, is providing all these sort of tools, giving you assurance on reliability and comfort for your users and clients, while allowing these innovative applications. And by providing this robust ecosystem of other campuses implementing these technologies in an open way, it's accessible, and you can do this at your campus as well. And if you're still not sure, certainly reach out to us. We can help. That's all I had.
Okay, we have about 5 minutes that we can get through some questions. Again, if we don't get through all of the questions in the next 5 minutes or so, these questions will be answered by directly to the person asking the question from the presenters. Our first question is, are the EUI data site energy or source energy?
So fortunately, the University of Toledo is set up as one big site. Basically, we own our own substations. So there's one for main campus, health science, and then Scott Park is considered a sub, even though it's within a Toledo Edison distribution area. When it comes to source versus site, you might want to take it back to the gas, nuclear, coal power plant and talk about the line loss and add that all in from the sustainability point of view. But for my what is the campus doing and how the campus is performing, I start at the substation. And natural gas wise, most of our campus relies on this it has a capacity of 160,000 pounds per hour, but really we run about 72,000 peak in the winter, and I'm referring just to main campus. So I can look at the main campus substation, and I can look at the gas use at the steam, and I'm getting 87% of everything associated with main campus. So those EUI numbers are real true to what comes into the entire campus. It's not convoluted by adding up a bunch of individual buildings.
Thank you. Our next question is regarding the amount of space required for the PV and BESS. Did you have any concerns with property tax implications?
Yes. But you're going back to 2007 when we were first building the field, and as one of the last people around, I don't remember. I know that there was some problem with taxes back then. We are a state entity, and it is a PPA field, but there was a problem back then. I don't recall exactly what it was.
Okay, well, thank you. What parts of MESA standards are you using to control the BESS?
So the best controller is implementing largely the MESA device standards, especially with regard to the battery systems themselves. The inverter that we have is actually not MESA compliant. We built the controller in a way as to be extensible and built it around the idea that it is primarily being used with MESA or MESA-like systems. Now, VOLTTRON does have a separate agent which handles communications for MESA ESS, and the goal with the BESS agent is to implement further modes that would be potentially used with that. They're not there yet. If I may interject one other thing before we run out of time completely here, that despite multiple reminders from my conscientious PI, I somehow skipped at the beginning of our presentation. I would like to point out that our work is graciously funded by the Department of Energy, specifically the Buildings Technologies Office at the excuse me, at the Energy Efficiency and Renewable Energy and the Office of Electricity, and it comes through PNNL, Pacific Northwest National Laboratory, and we are very thankful for our grant sponsors, and that's what I get for not having a separate slide for that.
We have time for just one more quick question. Just to confirm, VOLTTRON can be used to change BAS set points. What else can VOLTTRON be used to actively change something within the BAS?
So it can be used for anything exposed by the communications protocol you're using. So a lot of people from a safety perspective do like to just use the set points, because that means there's little chance of you affecting the automatic control system you already have in place. But it can certainly be used to control, any property exposed. We like to use BACnet, but it supports some other communication protocols as well. And it can be, it's just that from a safety perspective, not necessarily physical safety, but safety to your mission of providing a comfortable, or in some cases, maybe it is safety related to airflow or those sorts of things. Changing a set point tends to be the best way to implement that.
All right. Well, thank you so much. We're at the top of the hour here, so the questions that we did not get to will be answered by the presenters in a separate email to everyone. Gentlemen, thank you so much for taking your time to do this presentation. Attendees, as always, thank you so much for attending, and we look forward to next month's presentation, which will be on the OSHA top 10 things that they find or find wrong on facilities. So again, thank you very much for your attention, and we look forward to seeing you soon. Bye-bye now.
Thank you, Billy. Thank you for your time.
You're welcome.